So today we're going to talk about solving logarithmic equations. What makes a logarithmic equation? That's when our unknown value of x is inside a logarithm. So for instance, if I wanted to know log of what value would give me exactly 6, now remember this log would be the common log because they didn't write the base, so that would be base 10. And we'll talk about there are basically two different methods that we can use to do this. Okay, so steps for solving log equations. Number one, if there are multiple logarithms, use the properties that we use to expand and condense, but specifically to condense them to one single log. So we're going to condense them using those properties, the product rule, power rule, quotient rule from last time, or 2 classes ago. Decide which of the following 2 strategies to use. So if I can get one logarithm equal to one logarithm, so one log on each side. Okay. Now they have to be the same base for this strategy, but they will be most of the time anyway. But if we can get one log equals one log, then basically for these to be equal, those values inside or expressions inside, x and y, have to be equal. So set the values inside equal, finish solving for the variable. However, logarithms, as notated here, have some restricted values. Number one, the most important one that we'll see, is that the inside of a logarithm, like if I plug x back in or my variable back in and simplify that expression, it has to stay positive. It cannot equal 0. It cannot equal a negative number. So if you get a value of x that makes the inside 0 or a negative number, you got to throw it out. Extraneous solution. So you throw that answer out, and that might mean there's no solution. Okay. The base also has a restriction. It's supposed to be a positive number that doesn't equal 1. Okay, or has to be a positive, not equal to 1. Now the value outside the log, like if it equals a number, that can be anything. Okay. All right, so we do have to check our answers for log equations because we have this restriction. All right, so let's try number 5. First thing I see, sorry, I only talked about method 1 here, apologies. Method 2 is if you get one logarithm equal to a number. So if we have a number floating around, if I can condense to one log equals a number, we're going to change it from this form, which is log form, to exponential form. And that's why at the beginning when we did intro to logarithms, we spent time kind of converting between one and the other. Okay, so let's take a look at number 5. Our first example here, I see we've got multiple logs on the left and a log at the right. This looks to me like we're going to try method 1. Let's make one log equal one log. But on the left, we have more than one log. So we need to combine these using the product rule. And remember, the product rule says I can combine these two into one logarithm if I multiply their inside values. So 2x times 3 gives us 6x. And now we have one log equals one log. And what we can do is take the values inside, 6x, and set it equal to x minus 10. So let's get our x's on one side of the equation, maybe subtract x over. 6x minus 1x gives us 5x equals negative 10. Okay, divide by 5, and we end up with x equals negative 2. Okay, well, let's plug that back in. So if I plugged back in here, 2 times negative 2 would give me negative 4. And I can't have a negative value in here. So I'm pretty sure we have to throw this out. In fact, even if you plug it in here, and not only am I pretty sure, I'm positive that we have to throw this out. If it makes any logarithm value negative, we have to throw it out. So in this case, that's an extraneous solution, which means, because there was only one possible answer and it's an extraneous solution, it's a restricted value, that this problem actually has no solution. So our very first problem, man, no solution possible. Okay, but we learned a little bit about our strategies there. Let's take a look at number 6. Here we've got some logs on the left and a number on the right. I think my goal is method 2. Let's get one logarithm equal to a number. So we will need to condense these on the left again. And once again, because they're being added, we can use the product rule. So we can write them as one log if we multiply their insides. X times 4x is 4x squared. Okay, so now we've got it. One log equals a number. And when we're doing method 2, my goal from here is to change it to exponential form. So remember, the base of my logarithm is the base of my exponent, and the value of the log equals is the exponent. So 2 to the 6th value equals 4x squared. Now, 2 to the 6th value, you might need a calculator for that, but this is 64 equals 4 times x squared. Let's finish getting x by itself here. Divide both sides by 4. So now we end up with 64 divided by 4, which is 16, equals x squared. Square rooting both sides. Don't forget to do plus or minus. We end up with plus or minus 4. So we actually have two possible answers here. Positive 4 and negative 4. And we actually need to check both. So if I plug in positive 4 there, we just get 4. That's okay. If I plug in positive 4 here, 4 times 4 would be 16. That's positive, therefore that's okay. It's not a restricted value. However, negative 4, when I plug in, is not going to work, right? If I plug in negative 4 here, that's negative, and I can't have a negative value. So throw out negative 4. 4 times negative 4 would be negative 16. Can't have that either. So in this case, only positive 4. Negative 4 is an extraneous solution. We got to throw it out because it makes, when I plug it back into my logarithm, it made the inside negative. Okay, let's try a few more examples. I'll just copy kind of the methods here at the top. So first thing I see is we've got a logarithm over here and we've got a bunch of numbers floating around. I don't think I can get 1 log equals 1 log because, well, first of all, I only have 1 log in total, so I can't get 1 log on each side. So my goal then, I think, is going to be method 2. Let's get this 1 log equal to a number. So my goal here is going to kind of be to get this logarithm by itself. So let's get rid of those things on the left-hand side. Let's subtract, get rid of things with addition or subtraction. So subtract 4 on both sides. Negative 2 times the natural log of 2x minus 1 equals negative 10. Okay, let's also get rid of that negative 2 in the front that's held with multiplication. Let's divide that away. So these cancel out. We get the natural log of 2x minus 1 equals 5. And now we've got 1 log equals a number. Perfect. We've gotten to this point. Let's change it to exponential form. Now, if you remember, the natural log, the base of the natural log is that number e. So when we write this, it's going to be e to the 5th power, e to the 5th power equals 2x minus 1. Okay, that's log form, exponential form. Now we do need to finish getting x by itself here. We could calculate e to the 5th. First, keep a few extra decimals, subtract 1 and divide by 2. We can even do this as an exact answer. Check this out. We could just add 1 over. I like this way better because we can write it as a nice exact answer. 2x equals e to the 5th plus 1. Well, I need to get rid of that 2 held to x. Let's divide everything on both sides by 2. And so in fact, this answer, e to the 5th plus 1, all divided by 2, is our approximate value for x. Now, how do I know if that keeps this logarithm positive or negative? We're going to need to go to our calculator. So here's our Desmos calculator. I'm going to hit / for divide. And in fact, if you type e in, it knows you mean the number e to the 5th power plus 1 all over 2. Okay, so here's our approximate value for x. If I were to plug that in, so our equation is 2 times x, so 2 times the answer, so this is going to plug in the previous answer, minus 1. We just want to make sure this stays positive. Okay, and it does. It stays positive. So the inside of this logarithm would be positive 148. That doesn't, it's not a restricted value. So we can leave it as this exact answer, or as our decimal approximation, we can say about 74.707. 74.707 is our approximate answer for x. Now again, if you want to double check if this is completely the right answer, not only that it's not a restricted value, we could type in the whole thing and see if this is true, right? So let's instead say if I do -2 times the natural log, which is under functions, the natural log of 2 times our answer minus 1, and look at that, it does equal, oops, I forgot my plus 4, didn't I? Sorry, plus 4 does equal, there we go, -6. So our value of x does give us back -6. Perfect, I like it. Okay, let's try one more here. Example 8 is going to be a little more difficult. That's okay, we can handle it. In fact, look at this, it's already set up for method 2. 1 log equals a number. So let's go from log form to exponential form. 4 to the second power, 4 to the second power equals, ooh, this ugly fraction, x squared minus 4 over x minus 2. All right, well, 4 to the second power is 16. And what we're going to do is actually put this 16 over 1. We can take this rational equation and we can treat it like a proportion where we can say cross multiply. It's probably going to make our lives a little easier here. So we're going to end up cross multiplying and distributing as we go. So I'm going to do 1 times x squared first. 1 times x squared is x squared. 1 times -4 is -4. Equals 16 times x is 16x. And 16 times -2 is -32. And if you look at all these terms we've got, I've got x squared, x to the first, a couple constants. We have a quadratic. This guy is a quadratic. So we got to solve another quadratic. This is why we've been practicing all year. Let's move everything to the side where x squared is positive. And we're hoping that when I move this 16x over, there's no one to really line them up with. And add this 32 over. To set my equation equal to 0, we get x squared minus 16x. -4 and positive 32 make positive 28. That this is factorable. We're hoping this is factorable. Are there factors of 28 that add up to 16? What are my factors of 28? You got 1 and 28, 2 and 14, 3 doesn't go in there, 4 does 7 times, 5 doesn't, and 6 doesn't, and 7 would be a repeat. So are there any factors of 28 that add up to 16? And in this case, yes. So if we do an x factor here, this should work. We don't need to use like the full quadratic formula or something like that. So let's do our x factor. They got to multiply to positive 28, and they need to add up to -16. So that means to multiply to positive 28 that they are the same signs, and to add up to -16, sorry, they are both negative. And our pair is 2 and 14, so -2 and -14. And yep, they multiply to positive 28 and add up to -16. And if I set each factor equal to 0, we would get positive 2 and positive 14. So we got 2 answers to check, possibly 2 answers in here. However, ooh, I'm looking at one of them already. 2, I think, is going to cause us a problem. Look at what happens when I plug it in here. 2 minus 2 is 0, and now we're dividing by 0. I think that's a restricted value already, but let's check them. Okay, so here's just the inside of the logarithm. I haven't even typed in log yet, but if I plug in 2 in that expression that's inside the log here, it's undefined because, again, the bottom is 0, right? So we got to throw out 2. 2 is an extraneous solution already. Sorry, 2. We're hoping 14. Let's pull for 14. So if we try the same thing, let's plug in 14 here. It's 14 squared minus 4, 14 minus 2. Okay, that's a positive. Oh, and it's a positive value. So inside my logarithm, now remember, Desmos doesn't do base 4, so I would have to use change of base, which means I have to put this whole logarithm over log of 4. And check that out. 14, if I plug it in there, does make it equal to. So I had to use change of base. Remember the change of base formula? You drop the base, so the base of 4 goes in the bottom, and our other logarithm would go up top. So not only did I show that 2 was extraneous and 14 worked, but we even show it gives us the correct answer. So number 8, x is 14. Okay, we will definitely do much more examples of this in class. I'll try to keep it simple for the notes for now. Make sure you ask questions, and we'll see you in class.